Okay, perfect. Thank you for um, giving the floor to me. Just a couple of slides in order to allow ourselves. I'm the technical coordinator of the FLUIDOS project, so I'm going to introduce very briefly what is Fluido about. So the idea is that currently we have a lot of software that runs around and that can leverage the computing continuum. The computing continuum means that we can install and operate a software in different locations, like in the cloud, but also in the device or at the edge. And what FLUIDOS says is that we would like to guarantee in this computing continuum the same property of transparency that we are having in the cloud. So basically, let's imagine this very simple example. So a piece of software that acquires images and so on running on a robot, and another piece of software that runs in the cloud in order to do processing, image recognition, and so on. If we move the processing software into another cloud, so you move that, the acquisition software has to be reconfigured in order to talk to the other location of the processing software. So in other words, this is not transparent. So we would like to build in FLUIDOS a computing continuum that is transparent. That means if you have a software that is split in multiple pieces, like right now, in this very simple example, an acquisition part on the rover, a processing part on the cloud, we would like to guarantee the transparency, which means when the software is moved for whatever reason into another location, it still works without having to change anything. So this transparency property that we can guarantee within FLUIDOS. How do we achieve this? Basically, we start with many devices, many clusters at the edge, at the telco edge, or in the cloud. And we assume that at the beginning, all devices and clusters are, let's say, isolated. So this transparency property can be guaranteed within the cluster itself. What we do, we extend this software with FLUIDOS. So we do not change the base software. The base software still remains as it is. So the basic operating system, the basic software layers that for us are Kubernetes. But we add one more piece, which is FLUIDOS. We can create this kind of dynamic computing continuum. The dynamic computing continuum is not everybody can talk to everybody. It would be a huge mess. It's a kind of dynamic, like what is shown in this picture. So we can actually create small slices in which this transparency property exists. So like in this case, we have 2 or 3 clusters, whatever cluster means, that can be aggregated and seen as a unique, let's say, environment where the transparency property exists. Of course, the entire world is available, but what we feel is that the entire world is not a single gigantic cluster. It's just a list of clusters, a list of resources that we can have available for us to create this, let's say, transparent computing continuum. And then the transparent computing continuum is built selecting the most appropriate clusters within all the available ones. Which makes this is extremely scalable and can be controlled with policy and all the other stuff and security, of course, that we build in FLUIDOS. And basically, this is the end. Just a few words for the very edge of the spectrum, because we were talking about clusters. So of course, cloud, of course, servers, in some extent also devices, but definitely not Internet of Things. A small device in the Internet of Things cannot be considered as a cluster. So what we do here is that we have an extension for the very edge. So we use a different technology that seamlessly integrate with us, and where in the say let's cloud-based space we can share resources and services. Resources means I can use your CPU, your graphical processing unit, and whatever. In the left side of the spectrum here in the Internet of Things, we do not share physical resources, but we share services, and also some, in some sense, physical resources are, let's say, remapped into services using a technology which is well used in the enterprise and in the world, which is the Cube Edge. So this open source project that we leveraged. And that's all for my side, just a brief introduction of what FLUIDOS is about. And then, of course, there is orchestration, energy, because this elasticity and this transparency allows us to play nicely with energy savings or to burn less carbon, fuel, and so on. It's security, because the continuum can be extended across other domains, other regions that are not under our control. So, you know, security and trust is very important. But I will give the floor to our use case owners and our collaborators within the FLUIDOS project in order to show what they are going to do and what I have done actually with this basic piece of technology in order to solve their own problems.
Andrea, the floor is now yours. We would appreciate if you could introduce yourself again, because not everyone was in the meeting when we started originally. Thank you.
Okay, so thank you. So I am Andrea Detti. I'm professor in University of Rome Tor Vergata, and we participated to the first open call of LICO. No, sorry, not LICO, of FLUIDOS, and yeah, so we made. We participated at an extension project, so we try to add new functionality to the FLUIDOS platform, and specifically what we have done is, assume that you can see my screen now. What we have done now is we have extended the FLUIDOS framework with service mesh functionality. So we have introduced find a way to land service mesh features on FLUIDOS multi-cluster. And we also, what we have done is we have proposed, let's say, a way for a methodology for managing microservice application that are deployed in the edge and in the cloud, where the use of the edge computing is meant for reducing the latency. So in my presentation that I'm going to do, I provide you some initial, some general concept, general technical concept about our work, and then I have a hopefully small demo. I will try to, of course, do my best to fit within my my 20 minutes slot. And so why a service mesh? Why to introduce a service mesh in FLUIDOS, or in general in a Kubernetes application? Well, because service mesh provide built-in observability. This means that you develop an application, and if you add service mesh to this, if this application run in a Kubernetes cluster where there is a service mesh running, you have a lot of telemetry data, like metrics, logs, traces, and you get this information without any change in the code. So it is practically for free. Moreover, with service mesh, you can distribute the traffic among replicas of microservices in a much more advanced way with respect to the random load balancing of Kubernetes. And for instance, with a service mesh, you can implement a layer 7 strategy that prefer local microservices and only go away from your cluster towards another cluster if the microservices are not available in your cluster. And this is a kind of locality-aware load balancing that is fundamental for edge computing application. Without this, it is super risky to deploy at the edge something, because it can even worse. I will show the latency. And moreover, you can also within the internal, also if you do not have a multi-cluster solution, but you just work in a single cluster, with the service mesh, you can use a very nice load balancing strategy that is named the least outstanding regex, that definitely outperform the random load balancing of Kubernetes. Another advantage is that I see, of course, there are many advantages. Those are the advantages that I see in my experience. So another advantage is the connection persistence. This means that if you have a service mesh running in your cluster, what you have is that microservice among each other talk with persistent connection, regardless the fact that you have implemented persistent connection in your software. So, and this of course reduce the latency, especially if you do not have implemented persistent connection in your software, because this avoid every time the three-way handshake of TCP/IP. And last but not least, also if you do not have implemented any, let's say, TLS communication among your microservices, this is offered for free in case you land in a cluster where you have a service mesh installed. So every communication in the service, when you have the service mesh, rely on HTTPS or in general TLS, and this is added for free. Yeah, so this is some motivation about. So a question is that a question that I asked to myself, but then I think that is useful to say something about is why. So I used as a service mesh. I've used the Istio, is a famous service mesh, and famous service mesh, successful service mesh framework for Kubernetes. And one question is why you have to use Lico and Istio or together. So first of all, I want just, of course, you know, but it's better to introduce maybe that Lico is the multi-cluster framework that create the glue among different clusters in FLUIDOS. So Lico provide multi-cluster functionality, but for instance, Istio as well provide multi-cluster functionality. So why do not use directly Istio and instead use Lico and on top of Lico Istio? Well, I want to just state that first of all, Lico is and therefore FLUIDOS is protocol agnostic, so provide a protocol agnostic connectivity. So in my opinion, in my experience, it works at layer 3, and so you can have any microservices running not necessarily on HTTP, but also TCP, any TCP, UDP, let's say communication is supported by Lico. Unlike differently, if you implement multi-cluster with Istio, Istio is based on a layer 7 multi-cluster solution, and so it works well with HTTP and gRPC, but is seriously limited with UDP traffic and doesn't work actually in case of multi-cluster. Moreover, with LICO and therefore with FLUIDOS, we have full support of federated application. This means that LICO is more, let's say, useful for a federated environment in which there are tenants in which there are, let's say, stakeholders that want to offer portion of their cluster capability to other, the concept of consumer provider. Instead, Istio multi-cluster is not for, in my opinion, is not for federated environment. It's for a manner where you have two clusters and both clusters are of the same stakeholder. Okay, and yeah, so okay, so this is how we deployed, how we suggest to deploy. Of course, this is the way that we propose. There could be other way. The way how it is possible to deploy Istio on top of FLUIDOS multi-cluster, and we propose to in our architecture we have a single Istio control plane deployed in the cloud cluster that is the consumer cluster. We are I remember that we are considering edge computing where we have a cloud data center and many edge data center. So we propose to deploy the Istio control plane in the cloud cluster together with the observability stack made of Grafana, Jaeger, Prometheus, and Chiali. And on each cluster, we deploy Istio ingress gateway that actually are like Kubernetes ingress functionality. And the node of each cluster should be specifically tagged with a topology label. Like, for instance, the node in this edge cluster, that is the edge cluster number 1, should be tagged with topology, Kubernetes, IO zone, edge 1, and these nodes as topology, Kubernetes, IO zone, cloud. And yeah, so when you have deployed this, you must enable, if you want to efficiently support edge computing application, a feature of Istio that is named locality aware load balancing, that, as I mentioned before, prioritize traffic to local pods, reducing latency at inter-cluster traffic. And yeah, so just a few technicality on who is familiar with FLUIDOS and namespace of flooding. So this is the cloud cluster. This is the edge cluster. These are the node of the cloud cluster. This is the virtual node that represent the edge cluster. And so you have to tag, to label this node with the label cloud, this node with the label edge, this node with the label edge. And then you have to offload the Istio system namespace on the cloud cluster so that the Istio control plane is installed here. Istio ingress cloud namespace here so that the Istio ingress is deployed here. Istio ingress edge here so that it is deployed here, and the application namespace local and remote, because some microservice could be here and some microservice could be there. We focus at this scenario in which we have a microservice application, for instance, made by light blue, orange, and another microservice here, and purple. And a purple microservice. Some microservices like light blue and purple run in the edge cluster, and instead we assume that the whole set of microservices run in the cloud cluster. So we have some, practically we are focused on a scenario in which some microservices are replicated at the edge. Why? Because we have to consider that in an edge computing scenario we have many edge, and in one edge I can run, for instance, light blue and purple, and in another edge I can run only light blue. So overall, we think to a scenario in which we are considered a scenario in which we have all microservices that run in the cloud cluster, and few microservices are offloaded on edge clusters in an opportunistic way in order to ensure a specific request latency. And okay, so I don't want to. There are some other details, but I want to skip those other details to move to a small presentation in which I am going to deploy this kind of microservice application. It is a benchmark microservice application created with this tool that is named MoveBench. So it's a microservice. What is shown here is the dependency graph of the microservice application. It means that the user call the microservice number 0. So the user make a request to microservice number 0. Microservice number 0 make a request to microservice number 1. It make a request to microservice number 5, number 7. When number 7 reply, 5 asks to 6. When to 6 reply to 5, 5 reply to 1. 1 replying to 0, and so forth. So this is the dependency graph. So this is a benchmark application, and therefore there is a calling probability. So when a user calls 0, 0 call 1 with probability 0.3, and the same story, 1 call 5 with 0.3, and so forth. So it's so that for each request we have a random span of the microservice dependency graph. And each microservice stress the CPU only. Okay, so what we have now and what we have. So now we have, I need to remove this, okay. So, okay, so what we have now, we have two clusters. One cloud cluster and one edge cluster named edge 1, and let me try to okay, I put this in a better way. So we have a cloud cluster, we have an edge cluster, and among the cluster we have 1 gigabit of bandwidth and 160 milliseconds of round trip time. This configuration is emulated on OpenStack, and Istio and related ingress gateway has been already installed, as I mentioned before. So now I want to deploy this application here. So first of all, I need to create the namespace like this. Oh, sorry. I need to create a namespace. Okay. Okay, now the namespace is created. I need to offload the namespace. And so that it, in this way, this namespace can run a microservice on the cloud and on the edge. And currently, then I deploy the application only in the cloud with this command. Okay. Okay, so now we have the application that run in the cloud only, and currently. So demo effect. Okay, currently there is no Istio support. Okay, so this is so the idea of this demo is to show you what happened without any service mesh and what happened when you run with service mesh and you use the service mesh as we recommend. Okay, so now we are in the phase no service mesh. Okay, so we have deployed this application. This application has 2 replicas of the microservice S0. The other microservice has only 1 replica. This is the dependency graph. Okay, and so this application is only in the cloud cluster because in the deployment we have inserted some affinity on the topology. Okay, and as you can see, this application is only in the cloud cluster, node cloud. Okay. And now I'm going to load the application from the computer through which I'm speaking. Okay, so I am generating a request flow to the okay, error 100%, perfect. Okay, maybe it's not time to debug now this. Okay, but fortunately I have the no, of course we have to run also something else. Okay, now we have deployed the application. We have to install the ingress rule. Okay, so what I have done now, I have skipped this step. What we have done now, practically, have configured this ingress because we are sending requests to this ingress. Okay, okay, now hopefully retry. Okay.
Andrea, I believe that you are not sharing something.
Okay, no, not sharing since when? I lose.
Since the demo effect happened.
Well, the problem is that okay, I got it. I've lost share. Okay, share. Okay, can you see now?
Yes, we can now.
Okay. Okay, good. Okay, so I have created the namespace, executed deployed the application at the edge and in the cloud. Okay, and this is the current status. Okay, so you see that we have the application running only in the cloud. Now I am loading the application. Okay, and what I observe now is a delay in the order of 440 milliseconds. Okay. We can also see some performance, for instance, accessing Grafana. So this is a Grafana dashboard in which I see, for instance, in this plot, I see the delay experienced by the user. Okay, is the delay of the service S0, that is the root service, then it calls other microservices. But consider S0 as the delay experienced by the user. Currently, in this configuration, no Istio, all in the cloud, okay, we are experiencing 450 milliseconds of delay. Now, what we can do is we can say, okay, so let's move some microservice, let's move, for instance, some microservice at the edge. Okay, so and we can run this command and to execute some microservice at the edge. So now we have microservice S0, S1, S2, and S3 as the edge. So practically we have replicated at the edge 0, 1, 2, and 3. Okay, so and what we have now is that we have so this microservices run at the edge and at the cloud. Okay, so we can see that S0 run both at the edge, both at the cloud and at the edge. Okay, so we have replicated them. So let's move back to see which are the performance, and surprisingly, performance worst. So be careful. Edge computing without careful use and with the random load balancing of Kubernetes can worsen the delay. And this is a proof of concept. So you can say, how is this possible? I'm moving microservice at the edge. I'm using edge computing because I want to reduce the delay. And what I end up is an increase of the delay. Yeah, so this happens because we do not have a service mesh with that provide locality load balancing. Okay, and so what is going on is that when we have some an instance of S0 that run in the edge and an instance that run in the cloud, we are using plain Kubernetes. It uses random load balancing. So sometimes a request of the user go on the version of S0 running in the edge, but sometimes go in a version of S0 running in the cloud. Then S0 call S1. But since the random load balancing, it can call S1 that run in the edge. And so you risk to go back and forth from cloud and edge many times. And so you risk to make the performance worse. Okay, that's the problem with random load balancing. And when you have the same service here and there. That is a usual configuration in my opinion, okay? For edge computing, of course. So, okay, so now I have shown you the bad of not having an Istio service mesh. So first of all, we have few, so okay, it is down, but anyway, we have an increase in the delay, okay, from here to here, okay? Okay, so we have two bad. First of all, we risk to increase the delay, also in this case. And the second is that you see no information here. If you open this tool, you see nothing, okay? So you are a bit blind in terms of telemetry, and you can even worse the performance, okay? Now let's see what happened with Istio, okay? So, okay, so let's, of course, okay, so now I have, let me stop this, okay? Okay, let me remove this from the edge. I have to clean a bit. Okay, let me remove the app from the cloud. Okay, now let's wait a bit. Okay, now we have no application running. So first of all, we enable the use of Istio for this application in this way. Okay, Istio for this application enable. With this line, we enable locality load balancing. Okay, locality load balancing created. Now let us deploy the application in the cloud. Okay, so we deploy the application.
Andrea, sorry, we lost once more your screen.
Okay, let me again share. Oh, thanks for telling me. Okay, so I have enabled the use of Istio in the service for the namespace of the application. I have enabled with this line the locality load balancing. With this line, I have redeployed the application. Okay, and we can see key get pods dash and FLUIDOS mesh. Okay, so we can see that it is running in the cloud, the application. We see 2 of 2 because I have skipped something, but the service mesh, let's say, the concept, the technical concept behind the service mesh is that with a service mesh, each pod as an injected sidecar proxy that intercept any incoming request and outgoing request, and it make the magic of gathering telemetry and performing advanced load balancing strategy. So for this reason, you see 2 of 2 because there is not only the container of the microservice, but there is also the sidecar container for the service mesh. So currently now we have the application running in the cloud only, but with service mesh support. Okay, which are the advantages? Okay, so let me restart the traffic. Okay, so now I have restarted the traffic. Of course, there is no advantage in terms of delay. So this is just an initial burst. Because at the end, they will flat in the same previous value, okay? Because currently, the service mesh is not helping edge computing because we are not implementing edge computing. We are no microservice at the edge until now. But only just for single cluster application, you can see now that, let me, hope that I'm sharing. Okay, let me refresh a bit. Now go here. So I have this terrible. Okay, so if I go here, replay. Okay, so what we can see now. So before we are blind. Now, with, for instance, using Chiali, that is another telemetry tool, we see with Chiali the structure of the application. So we see that the application is made of S0, that call S9, that call S1, and we can go here, for instance, and we can monitor the total number of requests per second and so forth. Okay, we have many information, and this is for free, just because we are added the service mesh. Okay, and not only, also if we use Grafana, we have much more information. Before we have only this. Now you can see how much more information we have. Okay, so we have, for instance, the request rate of each service running in the cloud. We have the delay, not only of S0, that is the delay experienced by the user, but we have the delay also of each other microservices. So we can measure each cloud traffic. So we have much more information. Okay, and this is the advantage. And not only with Jagger, we also have traces. So for instance, Jagger is a tracing tool. For instance, now I can, let me select, for instance, 13, 14, 59. Okay, though I can find traces. And so what is this information? These are traces. So if I click here, I know that there has been a request. This is the duration of the request. This request is made of sub-requests, and this is the duration of each sub-request. So S0 took 44 milliseconds. S0 called S2, that took 43. S2 called 40, then S0 called 43, and so forth. So you know each request, not each request, a subset of requests, which microservice called, the sequence of called microservices, and how long time. This is a fundamental tool for debugging microservice application, because you can understand who is the culprit, for instance, if something got bad. Okay, you are able to understand. And as you can see, this is provided just installing a service mesh. Okay, now let's see the effect on edge computing. Okay, so okay, so now I can download the 0, 1, 2, and 3 to the edge. Okay, with this command, that are the same command as before. Okay, now they are on the edge. Now let's move back to see the performance. Okay, so in the previous case, without Istio, we have bad performance with this action, surprisingly. So without Istio, edge computing risks to become a foe instead of friend. Okay, now let's see with Istio. Yeah, I can go here, I can go here. Okay, let me refresh, because this takes time. Okay, we have to, so first of all, we should see that the request rate for S0, S1, S2, and S3 drop down, because with Istio we have locality load balancing. This means that now we have S1, S0, S1, S2, S3 on the edge. So no one will call S0, S1, S2, S3 in the cloud, because the user is entering in the edge, find this microservice in the edge, and do not go in the cloud, like with Kubernetes random load balancing. And in fact, immediately, the requests for microservices that are also in the edge drop down to 0 for the replica in the cloud. Instead, for the request of those microservices in the edge, they grow. So they're capturing all requests coming from the user at that edge. And this, as we can see here, drop down the delay. The user delay is this one. So we moved from a cloud only a delay of 440 milliseconds to a delay of 200 milliseconds. Now cloud computing is an effective solution. Okay, but just because we have locality load balancing provided by the service mesh, and yeah, so yeah, I have now concluded my presentation. My remark is that if you want to use edge computing, be careful with the random load balancing of Kubernetes. Thank you. Okay, So I need to figure out, okay.
Thank you very much, Andrea. Nikos, now we will give the floor to you. And for the audience, I have a message. If you have any questions, please drop them in the chat. Andrea will be able to answer them in the meantime.
Okay, I hope you can see my screen.
Yes, we can.
Yeah, so hello. I'm Nikos Fotiou. I'm CEO of Exceed, and in this presentation, I will present you our project title, Identity and Access Management for the Computing Continuum. In this project, we leveraged the identity management components provided by FLUIDOS in order to build a flexible, decentralized authentication and authorization system. But first, a few words about our company. Exceed was established 2 years ago in Athens, Greece. Our company is a spin-off of the Athens University of Economic and Business. We are developing solutions for identity and access management, focusing mostly on business-to-business use cases. Additionally, we are developing traceability and security solutions for supply chain, focusing on software supply chains. And related to that, we are involved in a large-scale European project that will produce tools which will enable SMEs to achieve compliance with the recent Cyber Resilience Act European regulation. So our project began with the need to address the complexity of authorization systems that involve many different stakeholders. So we targeted to create a flexible solution for authentication and authorization that could work with any service that uses HTTP. Of which, of course, covers most of modern applications. Also, we aim to support continuous user authentication and authorization following the so-called zero trust security model, where no user or device is trusted by default, and therefore every request must be verified. On top of that, we wanted access control to be smart and dynamic, adjusting to the context of user or the protected resource being accessed. And finally, we wanted our system to fit the needs of real-world multi-organization environments by allowing each stakeholder to manage its own users and trust decisions independently, using a decentralized identity and policy management approach. So, to better explain the challenges we faced in our project, let me walk you through a use case that we used throughout our work. So, imagine a smart city with many Internet of Things devices. This could be smart cameras, energy meters, smart lamps, and so on. And suppose that all of these devices are managed by an entity, by the city hall. Okay. So now let's say that the city hall makes an agreement, an arrangement with a local university And as part of this agreement, users that have the role of the researcher in the university are allowed to access smart energy devices, and not all smart energy devices, but devices located in a specific area of the city. Okay, and suppose that these devices are accessible through an API gateway. Now, this setup obviously brings several challenges. First, we want the security rules to update automatically every time a new device is installed in the area that users can access. So we don't want someone to manually change the policies every time something changes in this area. And secondly, we want a simple way to give or take away the researcher role from a user. And this should not require going into the system and writing access rules and things like that. And of course, we want each organization to manage its own users and trust relationships. So, for example, the city hall should be able to decide which universities it trusts, and the university should be able to manage the information related to its own staff. So, a great fit for our use case is an authorization model called relationship-based access control. Now, this is a modern way of handling permissions by defining relationships between different objects and then building access rules based on those relationships. So let me give you a simple example based on the use case I just described. So in our system, we might have objects that represent users, locations, and devices. And then we can define relationships between them. So for instance, a user might have a can read relationship with a location, and a device might have a located in relationship with that same location. Okay, now what makes this model powerful is that we can also define rules for indirect or transitive relationships. For example, if a user can read a location, then they can also read any device that is located in that location. Okay. So once we set up this kind of model, we can create what we call relationship tuples. So these are statements like user Alice can read the location city center, or lamp 1 is located in location city center. Now, when a user tries to access something, we check the access by making a query like has a user Alice relation can read with lamp1, and then the system answers these questions based on the model, the rules that we have defined, as well as the relationship tuples. And in this particular example, the response will be true. But we want each stakeholder to be able to define its own objects and relationships. For example, the city hall should be able to define and manage the relationships between IoT devices, while the university should be able to manage the relationships related to its own staff. But we need a way to securely share the relationships defined by these two entities and combine them in order to build a full model that supports access control across different organizations. And to make this exchange of relationships possible, we leverage a technology called verified credentials, which is provided by the FLUIDOS identity management component. So verified credentials are different from the traditional model of authentication, where an authorization server sends user information directly to a relying party. With verified credentials, the authorization server, which is now called the issuer, gives the credential directly to the user instead. So a verified credential is like a digital version of the user attributes signed by the issuer and linked to a cryptographic key that only the user controls. And this credential is stored in a secure software component, usually referred to as a wallet. And then the user can present the credential to a relying party, which in the verified credential world is usually called the verifier, and prove that they own it. Okay, so in our use case, this brings some important benefits. First, the issuer and the verifier do not need to talk to each other during the verification of a credential, which make this process fast and possible even when the verifier is offline. Second, the user can combine credentials from different issuers, and this enables more advanced scenarios. For example, we can have policies that where users should be students of a university, but also residents of a specific city. Therefore, users can collect multiple credentials proving these attributes and request access. Beyond our use case, the use of verified credential enhance users' privacy, since an issuer cannot track user activities. This is very significant from a privacy-preserving perspective, but it is less important in our specific use case. And I want to highlight here that the FLUIDOS identity management component provides all the necessary software and libraries that can be used for implementing the functionality of all these roles. So let's now see how everything works together. Now, the university manages information about its staff using an identity management system. And at the same time, the City Hall manages access rules using relationship-based access control in a system called the policy administration point. Then each user receives a verified credential from the university that describes their attributes. And when the user wants to access a service, they include this credential and the proof that they own it in the HTTP headers of the corresponding request. Now, these requests are first intercepted by a proxy called the policy enforcement point, and the proxy contacts another component called the policy decision point to check if the user is allowed to make the request. Now, the policy decision point combines the attributes of the user included in the verified credential with the relationship-based access control policies and makes a decision. Now, depending on that decision, the request is either rejected or forwarded in the API gateway. So, to sum up, here are some key takeaways from our project. Using verified credentials allows each stakeholder to manage its own users and access control policies independently, while still supporting access decisions based on combined policies across organizations. Also, by separating by decoupling issuance and verification process, we can achieve fast and continuous authentication and authorization. I want to highlight that this was a very high level presentation of what we did during the project. And if you are interested in more technical details, we recently published a paper called Identity and Access Management for the Computing Continuum. And there you can find many technical details related to our project. Although this specific project has ended, we are continuing our work in this area. We are exploring how to combine these technologies to support other use cases, particularly focusing in business-to-business settings. We are looking into different protocols for managing the life cycle of verified credentials. So one challenge here is that because verified credentials is a new technology, the standardization large scale it's still quite fragmented, and there are different and diverse standards related to the issuance, presentation, and the coding of a credential. And we are also exploring the automation of access control management, where relationships are automatically generated, and therefore no manual definition of relationship tuples is required. And we are also working on new authentication methods, including the use of decentralized identifiers, as well as attestations generated by trusted hardware modules. And with this, I would like to thank you, and I will be happy to take any question.
Thank you very much, Nikos. Thanks for the nice presentation. Any question from the public? No. Okay, so I have one actually. So in your last slide, you presented also the paper that you wrote about your implementation and your research. And the title of the paper includes the word computing continuum. FLUIDOS is a transparent computing continuum. So my question is, did you find out any additional challenge because of this transparent computing continuum in your research, or vice versa, the transparent continuum simplified something in your work?
Yes, so it's the second case, and especially by leveraging FLUIDOS components related to identity user management, we were able to abstract a lot of complex things related to verified credential issuance and verification. And furthermore, because we had this decoupling of issuance and verification, we were able to support cases where this policy enforcement point was moved around in different locations, and the same access control rules could be applied and used.
Thank you very much. I think we can move to the next.
Yes, Alejandro, please, the floor is yours.
Yes, hi everyone, I'm going to share my screen. Okay, can you see my screen?
Yes.
Perfectly.
Okay, so hi everyone, I'm Alejandro Arias from a researcher from Odin Solutions, and we were actually one of the winners for the first open call for technology extension of FLUIDOS with the Shadatu project. Before going into the Shadatu project, I'm going to introduce Odin Solutions. So we, Odin Solutions, we are a SMA company founded in OS in 2014. We are accredited as an innovative technology company by Mineco, which is the Spanish Ministry of Economy and Competitiveness, and ANTES, which is the Spanish National Association of European Business and Innovation Centers. So here at Odins, we specialize in the design, development, and implementation, of products and solutions for monitoring, remote control, and automation. We also actively participate in research and development projects at regional, national, and European level. In terms of hardware, we manufacture our own device for monitoring and remote management. And with this device, we use different wireless technologies such as LoRa, narrowband, IoT, 6LoWPAN, and GPRS and Wi-Fi. But we also work with wired connections like Ethernet. To gather all this data from the hardware devices, we have a software platform called WeCloud, which offers a comprehensive and efficient solution for the users to enable smarter and more sustainable data-driven decisions. So actually, we focus on three main areas, which are the smart city, smart agriculture, and smart industry. In terms of smart city, we offer solutions for environmental monitoring, such as weather parameters and air quality or noise level in cities. Also for water resource management, for the water quality and leak control, waste monitoring, monitoring of public buildings, and also for smart garden. And then for the smart agriculture, we offer solution for crop and soil monitoring, and also the dendrometry for the crop, and also water resource management with smart irrigation and water consumption. And also we support supply chain monitoring for distribution centers and livestock in the agriculture. And finally, for the smart industry, we also offer product quality control for example, refrigeration chambers. So how is FLUIDOS relevant to Odin? So, well, basically, thanks to FLUIDOS, we have been able to develop and implement decentralized authorization and accounting mechanism. So FLUIDOS provided Odins with a framework, with an initial framework for the design, development, the development of the decentralized security and accounting mechanism. FLUIDOS also provided or allowed Odins to validate the developments in real testbeds. We have also the opportunity to collaborate with experts in the area of cybersecurity of the FLUIDOS consortiums, such as the University of Murcia. And finally, thanks to FLUIDOS, we have also been able to achieve a business and technical alignment in terms of implementing security functionalities for the smart city, smart agriculture, and smart industry. So let's now move on with what we have actually done with the Shadatu project for the open call. So basically, here you can see the overall components or architecture that we have integrated, developed, and integrated in the initial FLUIDOS architecture. I will explain later, of course, all components, component by component. But the main goal for the Shadatu project was to improve the FLUIDOS architecture in terms of security by adding decentralized authorization and accounting mechanism. These security functionalities were focused for the federated access control and and the traceability for resource distributed across the Gaia X continuum, and of course to address the security, interoperability, and transparency needs in highly distributed edge cloud environments such as the FLUIDOS project. So here you can see the XACML component. The XACML component is an authorization component based on XACML and attribute-based access control. So this component is divided into three components, which are the policy administration point. This component offers our web application for creating, modifying, or deleting policies and rules for the FLUIDOS domain. Then we have the policy decision point. This component evaluates the access request, and basically it's the one that issues the authorization decision, which can be permit or deny. And these two components, the PAP and the PDP, are deployed on the cloud. And then we have the policy enforcement point proxy, which is actually deployed in each node of the architecture, and it is used for basically verify that the access tokens provided after the authorization are valid, and then for the enforce of the PDP decisions. Then we also added some integrations, some developments for the hyperledger fabric blockchain. So FLUIDOS already offered an hyperledger fabric deployment. So we have to develop two new smart contracts for the blockchain. One was for the storage of XACML policies and attributes. So this facilities and guarantees immutability of and decentralization of the policies and rules of the XACML. And the other smart contract was for the registry of authorization request for the accountability. And this authorization request it can also be queried by ID, by timestamp, by the decentralized identifier, or you can basically use a custom filter to retrieve this authorization request. This thank you for the REST API server that we developed for the blockchain interaction. So this thanks to this component, we remove the need to have an application gateway component in each node. So it basically provides the access to the policy and attribute management, and in an easier way. So here you can see the authorization and accounting mechanism. So as I said, the authorization is based on XACML, and it also use the attribute-based access control. Both the authorization and the accounting of the authorization requests are stored in blockchain, as I mentioned also. So on the top right side of the screen, you can see the structure of the authentication request that we are currently storing in the blockchain. You can see that we add some important fields to, for example, the timestamp to know when the authorization request was made, the action, which is the HTTP action for the request, the resource, which is the resource that the node is trying to obtain, an identifier for the authorization request, the decentralized identifier of the node that it's making the request, then the subject, which is an attribute from the verifier presentation, and finally the decision of the XACML, which can be permit or deny. Then we have the access tokens, which are obtained after the authentication process. The authorization process. And this is issued by the node that verifies the unauthorized the node. The access token is used by the PIP proxy to validate and allow access to resource. And on the left side, you can see the structure of the access token. The access token is divided into two parts. The first part will be the header, which includes some key information about the algorithm used for signing the access token. And then we have the payload, which include information about the request, like for example, the decentralized identifier of who is making the request, the timestamp when it was issued, the timestamp when it will expire, the HTTP method, and the resource to be consumed, and the subject. Later, I will explain how everything works with the diagram. So basically, this is how the overall architecture looked before the Sadato project. So FLUIDOS and the University of Murcia already had implemented different securities components for the authentication, such as the privacy and security manager. The identity management includes the decentralized identifiers, the verified credentials, and presentations. And as I said, it's already there were developed some core components such as the verified data registry, the rear, and the privacy and security manager. So the limitation here was that there was not decentralized authorization. Actually, there were not authorization at all. There was only authentication. There was neither integrated accounting or traceability, and of course there was no authorization using DLT or attribute-based access control. So this is how it look now with our components that we have added. So in the red circles are the steps that were already implemented, and then the green circles are the steps that we added for the Sadato project. So as you can see, the authentication process ends on step 3 after the consumer node sends the verified presentation to the producer. The producer verifies this verified presentation with the DLT, and if it's verified, it means that the consumer is authenticated. So this is what was already implemented in FLUIDOS. So what we added was the authentication process that the privacy and security manager consists on the privacy and security manager consults the XAML for the authorizations. It sends the request, and the PDP is the one that enforced a decision based on the request that can be denied or permit. After this, the PDP has two actions. One is to register this authentication request on the blockchain, and the other one is to send the decision back to the privacy and security manager. Once the privacy and security manager obtains the decisions, if it is permit, means that the consumer is authorized. So it creates the access token that I explained before, which is basically the key to access any resource, or actually the resource that the access token was requested for. So the privacy and security manager from the producer sends back the access token to the consumer. The consumer stores the access token, and then it makes the request to the producer, including this access token on an HTTP header. So you can see here the PIP proxy is in front of the producer, so it basically is the entry point for the producer. So it checks every request made to the producer and checks the validity of the access token. If the access token is validated, then it forwards the request to a real component inside the producer. So how the PIP proxy verifies that the access token is valid? So it is divided in different steps. So the first step is to verify the signature. So the authors token is actually signed by the producer, which is who generated the authors token. After validating the signatures, it checks the different properties of the authors token. It checks if it has expired, or it also checks if the HTTP method included in the token corresponds with the HTTP method of the request received by the consumer. The same for the resource. And after all of this is verified, then the PEP proxy can forward the request to the real component. So basically what we have achieved by adding all these new functionalities and components is to include a distributed XACML based and attributes based access control authorization model. Also with the API REST server that we develop, we added some interoperability with different components. So as I said, we removed the need that every component has to execute the application gateway to connect with the blockchain. So we added all this functionality into this API REST server. So we added we gained some interoperability with this. We also added some transparency and auditability for by registering this authentication request into the blockchain. And also we have added some efficiency in terms of latency. At first, you may think that with all these additional steps, we are like delaying or increasing the latency, which actually is correct, but it is just for the first interaction. So after the consumer has obtained the access token for the next like the next time or the next times the consumer wants to consume some product from or resource from the producer, it will just send the access token. So at the long run, we are currently reducing the latency, because you don't have to, every time you want to consume some resource, you have to, we eliminated the need for having to send the verified presentation, verify, authenticates, etc. So once you obtain the access token, for all the next request, obviously until the access tokens has expired. But for the next request, you just have to send the access token, and you will be able to obtain the resource. So for the further development of this data project, we identified 3 areas that can be improved. One of these areas is to create new queries for obtaining authorization records. As I said, right now, the smart contract that we develop supports queries by the ID of the authentication request, the decentralized by the decentralized identifier, by date, and by custom filters. But it is, I think that it will be possible to develop more queries and to implement more queries, such as to obtain authorization records by policy type or by access outcome or resource type. So I think this will improve forensic and auditing capabilities. Then the other area is the creation of additional XACML combining algorithms, because right now the XACML only supports the algorithm first applicable, which the XACML goes rule by rule, and it is stopped when there is a match with one rule. So for the future week, I think it is possible to develop more algorithms, such as deny overrides, to focus on deny rules, to give priority to deny rules, or also the other one, which would be the permit overrides, to give priority to permit rules. With this, I think we will gain and we will enable more flexible and secure policy evaluation strategies. And finally, one that I think is the most important is add an access token revocation mechanism. So right now, it's not possible to revoke an access token that was issued because right now the access token has an expiration time, but you cannot revoke the access token. So I think that revoking access tokens will allow that early termination of access tokens in case of compromised credentials or some changes in policies or some rules that are updated on the XACML. And with this, I think we will improve real-time enforcement and adaptability of access decisions. So I think that's all from my side. I don't know if you have. Thank you for your attention. I don't know if you have any question or comments. Also, you have here my email if you want to ask something via email.
Thank you, Alejandro, for your very deep presentation.
Thank you.
It's very clear that you know very well what you are saying. And in fact, I'm going to ask you, let's say, a difficult question. So in your presentation, you forgot about, let's say, your grandmother. So let's take your grandmother now. So how would you explain this project? Which are the advantages that a normal user, not a technical people, would experience thanks to your work? Can you just summarize in a couple of sentences?
Yes, I think that
decentralized credential, but
yes.
Okay, for the normal people, what does it mean?
Yes, I think that which is more important to understand here for the normal people. I think that this decentralized like architecture and environment of security components is way more secure and than centralized security. So I think if you want to focus just on security, I would say that to have these decentralized securities by the use of Hyperledger Fabric as the blockchain and all these components, I think that it improves the security and also it reduces the latency in terms of security. At the same, I mean, it reduces the time for the verification and authentication process, which I think it's also quite important at the same time that we are adding more security as we are adding authentication and accountability. So I think that this the two most important aspects of this Sadato project.
Okay, thank you very much. And the second question is actually your company is focusing on precision agriculture. So how this project fits into what you're gonna deliver as a product, or I mean, what you can say, of course, I'm not gonna ask you.
Yes. Yes, I mean, as you said, we focus on precision agriculture. So we have a lot of hardware devices that we deployed on agriculture fields. So I think that we can benefit from the IoT to edge to cloud continuum here. So and also put the focus on the security aspect, which we think that is one of the most important aspect in this area. So I think that the use of IoT to edge to cloud continuum will improve our system in this agriculture and smart buildings and cities scenarios.
Thank you very much.
Thank you.
Any other question? No? Okay, so we can move to the next presenter.
Shabnaz, the floor is yours now.
So I will take the floor then for Shabnaz.
Thank you.
Oh, let me see. I requested the, there we go. Okay, so I think you can now see my screen, at least I hope.
Yes, we can.
Yes, okay. So hello everybody, thanks for the invitation and for the organization of this event.
Sorry, we
my
can
name
see
is...
the presenter's point of view.
That's
Cannot see the full
one
presentation.
moment. That's a good hint. One moment. Why? And that's the wrong one to share. One moment. Now it should be better, I hope.
Yes.
Yes, okay. So my name is Stefan. We applied for the FLUIDOS project with our new protocol, internet protocol, which we call Neuropil. And I'm just going to shortly introduce you to the Neuropil protocol before going into the collaboration with the FLUIDOS system. Next slide. So what is the Neuropil? The name is actually derived from the biology, and Neuropil is another name for the gray matter in your brain. So it's the material that surrounds all your cells, all your thinking cells, and it's basically the material that allows them to think. So it's not about thinking, but it's just the thing that sits between everything to allow communication between all the cells and so on. So we named our project according to this, and of course we have a few, we started already in 2016, and we always developed this protocol as a side project, but we always have some guiding principles, and you have already heard some of them in the last talks. One of them, of course, is zero trust. So using the identity as the parameter and not any kind of artificial boundary like internal or external zones, but really use the identity as the parameter to apply rules and to apply or to enforce rules and access control. The second influence that we have is the one from named data networks. So named data networks is an approach that basically claims that the IP addresses that we currently use is the wrong routing criteria. So by using the IP address, we actually add barriers that we don't want to have, and that it would be much better to use the real names of objects. That automatically also, if you have the name or if you have the hash value of something, then of course you also have data provenance because you know that this is the object that you would like to receive. That is the hash value of the object. So that makes a lot of things for the modern world a lot easier. We have one additional influence. You already heard Gaia X before. That is the data spaces area. That means we are talking about consumers and providers who would like to exchange data based on digital rights, and they would like to agree on certain rules how data can be shared before actually the sharing happens. And you also heard already about self-sovereign identities. Since everything in Zero Trust has a digital identity, then of course the switch to self-sovereign identities is very easy. And of course, we use verifiable credentials. So in our solution, we use CVT, that's the binary version of a JWT token, the JWT. And before actually anything happens, we create a fingerprint of this one. This is our verifiable credential that we can pre-share before actually sending the pre-image. So as a short summary, Neuropil is an internet protocol for the 21st century, and it's driven by security and privacy by design. Some of the features that we have is one of them is the end-to-end encryption and attribute-based access control. So before any kind of communication happens, we exchange the digital identities, and we can with the attributes, and of course we can then check whether the attributes are what we expect to be. In addition to enhanced privacy, there is no metadata or IP exposure. So I mentioned named data networks. We don't use IP addresses anymore as our routing criteria, but we use the hash values of the data channels that we would like to use. So of course we have protection against man-in-the-middle attack and replay attacks. And that means our solution is ideal for IoT, smart cities, cloud native apps, or hybrid cloud integrations. And that is of course also why we applied for the FLUIDOS. Before I step further, maybe let me show you something just to give you an impression how it works. I have to reshare my screen, I think. Okay. One moment, please. Okay, so now what you see now is like the graphical presentation. And of course, the demo does not work as expected. That is wonderful. I started it a few minutes ago and it worked. Okay, maybe I can show it to you later again. We have to see. Let's go back to. So let's go back to the slide. What is the common ground for our protocol and FLUIDOS? So FLUIDOS, from our point of view, is a flexible and secure system to connect different kind of clusters and actually also to administrate and to make the resources available to these to the other participants. So its main focus is on resource management. We also have LICO underneath it, which is about exchanging the necessary Kubernetes events to the other clusters that you can share the nodes. And that is what the core functionality of FLUIDOS is. And that, of course, gives you or brings you directly into a multi-tenant environment because you then have different kind of actors who are trying to share their resources or to share their workloads and so on. In European, in contrast, it's a decentralized identity and data exchange layer that I explained before. And we do direct device-to-device communication based on the hash values, based on the digital identities. And we have, we provide a privacy by design publish and subscribe protocol. And both projects, we have a common goal. So we would like to enable the European cloud continuum. So if you take the idea from Gaia X, that all the infrastructure providers can share their resources very easily, and you would like to basically just book resources very easily, that is done. So this booking and this administration part is done by FLUIDOS. But of course, you also need some kind of common addressing feature and a common transport layer. And that is something that in European could be. So this is our common goal that we identified. What did we do for the FLUIDOS project? FLUIDOS is having a so-called discovery phase. So in this discovery phase, it's trying to reach out and to see what other clusters are available in the network or even somewhere else. And then based on this information, it can exchange information about the so-called flavors. That is all part of the RIA protocol. And that means by exchanging this information, then the booking and so on can take place. So as I said before, several actors come together. So we are in a multi-tenant environment. And that means you have to act like in a multi-tenant environment. The Neuropil protocol with the end-to-end encryption built in allows to exchange this kind of information. And especially because we are a publish-subscribe protocol, we can act as a more efficient resource to exchange this initial set of information. So what we designed was we implement an easier discovery and data transfer across clusters, which is basically based on zero trust. So we have a digital identity of it. We can also then, all the participants can join the clusters or can join the FLUIDOS ecosystem, and then they can see which other participants are available, and then they can book. In addition, because our protocol is very lightweight with a JOT token, we can also seamlessly integrate IoT devices or IIoT devices. So IoT devices are the very small ones that could be a bit difficult. But for larger systems like robots, we also have a small robot showcase that we use. For this, we can easily also integrate it and connect it then to the different Kubernetes clusters. Here you can see our architecture that we wanted to do. You can basically see on the left and on the right, you see each cluster, each participating in the FLUIDOS ecosystem. And on the top left, you see the FLUIDOS resources, the custom resource definitions, and the FLUIDOS controller that we developed. So that is our contribution. And using this FLUIDOS controller, we can basically exchange the kind of discovery information, the known cluster information, and the flavor information. In addition, we developed some more core components, I would say. One of them, the Neuropil service, we developed it as a Neuropil privacy relay. So you can install it in every cluster, and it will basically install a small gateway component. It acts like the kube proxy that you know from Kubernetes, but it's just a privacy relay. So it's just a forwarding information from the different clusters to the destinations. So the Neuropil cybersecurity mesh that you see here in the middle, that actually is not like a central instance that is existing, but this is formed by all the different Neuropil services or privacy relays who share in the same network. That is what I wanted to show you earlier. Let's see if I can show it to you later. What we also achieved is that you can use a Neuropil native pod. And currently, we are working on the sidecar component that you can basically, similar to the sidecar component that is used in the Istio service mesh, that you can then basically install the Neuropil protocol in front of any kind of container to exchange the information and to inject the zero trust into it. So that was the picture of what we did. So here's a more textual representation. So we offer secure participation, for actors in a multi-tenant ecosystem. Because of the end-to-end encryption, everybody can share information in a decentralized way. We do the discovery of FLUIDOS nodes and resources in a decentralized way. And consumers of FLUIDOS resources. So if I'm a consumer or a customer of somebody providing resources like Kubernetes nodes or Kubernetes computing resources, then I can use them even if I stay behind my firewall. So I can sit on my own Kubernetes cluster, which I have deployed locally, and I can book the resources from other clusters which are available in the public, but I don't need any kind of public-facing components. because with the neural protocol and the discovery and the end-to-end encryption, I can do the communication anyway. And of course, that I already mentioned, the secure integration of IIoT devices, that is also possible. We had actually, unfortunately, not the time to elaborate this in our project. So how do we improve the FLUIDOS? Again, we are doing the discovery for multi-tenant environments. There is also a different discovery module which is using multicast, but that is not, that works well in local environments if you can have the multicast transport enabled. But our protocol can basically work between the different clusters more easily or in a different way than it was possible before. We provide a very lightweight digital identity solution based on CVT, so CBOR web token, the binary representation of the JOT token, and we can establish secure communication between nodes with these CVT-based authentications. In fact, all this sending of JOT token that happens in our protocol before any kind of communication happens out of the box. So you don't need to develop it or to install it. It will happen automatically. We enable end-to-end encrypted communication and therefore also a secure collaborative cloud-to-edge interoperability. And we can use a unified protocol from IIoT devices to cloud devices. And actually, with our protocol, you could say we bring a new kind of overlay protocol to the Kubernetes world. This time it's based not on IP6 or IP4. This time it's based on hash values. And then you can basically join any pods or establish any kind of communication path between pods or between services that you would like to. What is our further development? Currently, there is one master thesis running in our company. For secure communication, the issue that we found is that with FLUIDOS and LICO, you can basically share secrets with other clusters, but then also the administrator of the other cluster can also see the secret. So it's a bit a trust issue. How much trust do you have? But we see the possibility that you can basically delay the visibility of the secret until really your component that you would like to deploy on the other cluster is starting. And that it's only visible in memory, which is a different kind of thing than if it's visible as a secret in the Kubernetes cluster. The second point that we see, we would like to do an evolution of our solution into a gateway, a Kubernetes gateway. So Kubernetes gateways are the next generation ingress components for Kubernetes. So ingress components will be deprecated soon. There are already a couple of gateway components, and we see that we can basically act in a similar way, but with these additional enhancements that I've already presented. So to do this, of course, we need to develop our own CRDs, our own custom resource definitions for Kubernetes. We have started a bit in the FLUIDOS project, but since the discovery was our main focus, we did not push forward to it. And we also would like to have a sidecar container that is already on the way. And actually close to finish. So I hope that we can have this kind of sidecar container soon. We have to see if we can then use this sidecar container maybe together with a solution like Istio. But we have to elaborate this then in the future. Okay, so now my second attempt to show something. Let me see if that works now. What you see now is the discovery, how it is working. So first we log into our local cluster and switch over to the FLUIDOS namespace, of course. And then you can see that in the known cluster custom resource definition of FLUIDOS, there is no object. Or maybe I do a short break here just to show it to you a bit. You can see that there are no objects currently here in this one, in this area. So now what we do is we start our discovery component, and it will connect, of course, to one Bootstrap node in the internet. And of course, there's a second cluster running in the background as well. And after a short time, you see that now we have received this kind of known cluster information. And you can see that now the information is here in the objects. And now basically FLUIDOS can take this information and can do additional negotiations and contract negotiations for the project and to establish the contract. Okay, so that's it from my side. I will try to show you the other presentation or the other real live demo. But let me get back a bit into the background before showing it to you. Here are our contact details. So neuropil.org and neuropil.io are our protocol web pages. And of course, you have here our GitLab repositories. We also had one pull request to the GitHub repository of FLUIDOS. I'm not sure if that has been acknowledged yet, but I think there will also be some more improvement from our side. So we are still working and experimenting a bit with FLUIDOS. So that's it from my side. So maybe we can already start with some questions, and I'll try to fix my demo in the background.
Thank you very much, Stefan. Any question? No, okay. I have one question. Your component looks really, let's say, a very important component for our architecture, and thanks for your effort in developing this. The testing that we have done on your component shows that this component has some scalability problem in case we're running a large number of clusters, which is definitely much more than we can have right now. But in the future, this may be a possible issue that we have to tackle. Have you experienced similar problems from your side or not?
So we are a small company. We have only tested it with a very small number of clusters. What we decided is, so this kind of discovery is currently running or has been implemented to exchange information every minute. Of course, if you have thousands of clusters and each of them is exchanging its information each minute, then this is already a massive amount of information. Then we need to look again and to see whether we can enlarge or dynamically enlarge this interval, or to see if we can do other measures for this kind of discovery. Yes. I also want to mention, I recently, I think last week, I discovered one issue with our protocol, which basically forced it to drop connections. The point is that we scaled one of our Bloom filters wrongly, and that leads to loss of data connectivity. But that is solved now, so that will be solved. So that will be solved in one of our future releases. Yeah.
Okay. Okay. Perfect. Yeah, I'm pretty sure that right now the scale that you are supporting is more than enough for the current and for for future, let's say, closer future deployments. But in the far future, it may be worthwhile to think about something that scale even better. It's not something that is needed now, but because the protocol looks really nice from our testing, really nice. So having something that works even at the scale would be really wonderful.
Yeah. I can share now my screen again, I hope. That is what I wanted to show you before, and we also used it in our testing with Matteo. What you see is basically the nodes, how they are connected. So this is a real-life view. The node in the middle that you see is like a bootstrap node. And what I wanted to show you is that this node here, the brown one, can talk to this, what is it? Rosé colored node with the end-to-end encryption via the green one. And all of these, they have a digital identity, and they all, you can see, these are the fingerprints. This is like the verifiable credential. So they are addressable via this kind of identity. So that is how it looks. So I could now start more nodes if I wanted. And you can see that we measure the latency and the stability of the connectivity just to make it to make sure that we can reach our destinations. Yeah? That is what I wanted to show at the beginning. So just a short.
Thank you very much, Stefan. Let's move to the last presentation, last but not least, Stratos.
Hello everyone, just give me a second to share my screen. Okay, I think you can see my screen now.
Yes.
Yeah, okay. Okay. So hello everyone, and thank you for the opportunity to present today at this webinar. My name is Stratos and I'm representing 8bells. I'll be sharing with you how we contributed to the FLUIDOS platform through the fruitful open call, focusing specifically on enabling scalable machine learning operations or MLOps within the FLUIDOS environment. In this presentation, I will try to avoid getting into technical details and instead give an overview of the fruitful open call and what is provided to FLUIDOS. To begin, 8bells is an independent research and consulting company based in Nicosia, Cyprus, and Athens, Greece, and founded in 2016. We specialize in information and communication technologies and participate in a wide range of EU-funded projects, both under Horizon Europe and the European Defence Fund. Our area of activity includes 6G, artificial intelligence, machine learning, edge and cloud computing, cybersecurity, and Industry 4.0. This background makes us want to contribute to advanced infrastructure projects like FLUIDOS, especially when it comes to integrating and experimenting with AI and ML orchestration technologies. So our role in the project, FLUIDOS as a project presents a strategic opportunity for us to explore how orchestration can be extended across distributed computing environments. Within the FLUIDOS open call, our specific mission has been to bring robust MLOps capabilities into the FLUIDOS ecosystem. That is to enable artificial intelligence and machine learning workflows to run efficiently and reproducibly across FLUIDOS nodes and clusters. So to make this happen, we focused on two major technical integrations. First, we integrated Kubeflow into the FLUIDOS node. Kubeflow is an open source MLOps platform for managing ML workflows on Kubernetes. It provides a complete platform for machine learning pipelines from data processing and training to evaluation and deployment. It includes the Kubeflow pipelines for orchestration, Kserve for model serving, and the Katib for hyperparameter tuning for the models. Secondly, we integrated Feast, a feature store that manages ML features across workflows and experiments. It helps to, let's say, stabilize how features are defined, reused, and served during both training and inference, improving consistency and collaboration. Feast allows reusable, consistent feature definitions, historical feature retrieval for training, and real-time feature serving for inference. This ensures data consistency and accelerates experimentation. So what changed? Before Fruitful, Fluidos had a strong orchestration features and didn't include integrated tools for managing the machine learning life cycle. ML workflows had to be assembled manually without shared infrastructure or pipelines, and that could often lead to inefficiencies or inconsistencies. Oh, sorry. Sorry about that. So, yeah. So with the fruitful integration, we can now have a fully automated ML pipelines using Kubeflow, shared feature infrastructure via Feast, better use of models and features across nodes, and faster integration and better visibility into every step of the ML process. These changes not only streamline development, but make Fluidos more suitable for for developing real-world ML applications. The Fluidos continuum now offers dynamic offloading of ML services and jobs to any node in the network, leveraging a combination of telemetry and available resources. The system can intelligently allocate ML tasks, such as feature engineering, model training, and inference across multiple suitable nodes. This is enabled through integrated support of intent-based orchestration and resource-aware scheduling, ensuring the performance and cost efficiency and scalability across heterogeneous environments. So looking ahead, there is potential to build on this work. So we have a few directions that can be explored. First, aligning access control systems. For example, integrating Fluidos RBAC with Kubeflows and Feast RBAC would strengthen multi-user and multi-tenant scenarios. And second, this one I think is the more interesting one. It could be interesting to explore federated feature sharing, sorry. So this would allow features to be reused and shared securely across Fluidos nodes, using privacy-preserving techniques like secure multi-party computation or homomorphic encryption. So these ideas could move us forward to a more intelligent, secure, and collaborative FLUIDOS ecosystem. So that concludes my presentation. I think it was short enough and we are within the time frame. And thank you for the opportunity again to present. Let me.
Thank you, Stratos. So one question here. So you worked on machine learning and so on. So probably you needed also GPUs and so on. Did you experience with those kind of resources in FLUIDOS or not yet? In fact, there are other projects trying to work in this area in the next open call.
So we didn't specifically select suitable nodes with like a GPU constraint, but in theory this should be supported. We definitely selected nodes with CPU constraints and with I think disk constraints and file sizes, etc. But in theory, it should be supported. And in theory, also, it should. We also tried, and this should work with the GPU as well, to schedule, for example, some parts of a pipeline in some nodes and some parts of a pipeline in another node. So, for example, maybe when we are doing some feature, creating some features and cleaning some datasets, etc. Usually this requires more CPU power, so maybe you can schedule this on a node with better CPU, more cores, etc. And then when it comes to the actual training of the model, so this is like the second or third step of a pipeline. You can schedule this step on another node that has some GPU capabilities. So this should be supported, but we didn't test for it yet.
Perfect. Thank you. And a follow-up question, given what you said. Do you foresee a real necessity of this kind of transparent continuum, especially at the edge for machine learning and AI apps?
I'm not sure if I'm very suitable to answer this question because we're mainly focused on the research and innovation projects, so not so much for industry. But in my opinion, the strong point of FLUIDOS, I think, is that what you mentioned earlier for FLUIDOS enables the reusability of can enable the reusability of many devices that basically have very low power. So some old devices and stuff like that, FLUIDOS can connect them and uh, and basically use their power to maybe perform not the actual training, but maybe the cleaning of the dataset. For example, usually the dataset is can be divided in many different files. So even a computer that's kind of old can definitely process one file, for example, or 10 files or 100 files or something simple. So if you have many of those computers, even with this low power, you can make them work with each other with FLUIDOS and maybe do the pre-processing step, for example.
Okay. Thank you very much, Stratos.
Thank you.
Thank you, everyone. We appreciate your presentations. The meeting has been recorded and will be published on the project website next week. Have a good afternoon.
Thanks, everybody, for attending to this event.
Thank you all. Goodbye.
Thank you,
Bye.
everyone. Bye.